In IsolationForest, we dissect data hyperplane into regions, and then for each region measure how it is likely to have an anomaly within, basically creating an outlier likelihood heat map. IsolationForest is an ensemble method, so let's start by exploring its base algorithm, IsolationTree. The main idea of IsolationTree is to separate data points by drawing random lines. The easier it is to isolate a point, the more anomalous the point is. We start off by creating a root node containing all the given data points. Then we iteratively choose a feature and a random threshold value, specifying how we should partition our data. At any step, we can select for partition any node with at least two different objects in it. It is also prohibited to split the node in a way that one descendant node contains no objects. A node that cannot be partitioned is called leaf, and objects in it are considered to be isolated. By repeating this procedure, we eventually isolate all points. At that moment, we will count for each point its node's depth and use it as anomaly score. Remember, the deeper a node is, the less anomalous we consider its object to be. After the tree is fit, we assign to every region selected into a node anomaly score equal to the node's depth and use it for future prediction. For every test object, we will predict anomaly score of the region it is located in. To predict binary anomalousness, we will pick a threshold for anomaly score and consider points crossing this threshold outliers. But we have some problems. We got a solid cluster point located near center and a visible outlier attaining same scores. Also, the best score went to some cluster's body points. Because each tree is built randomly, its scores have tremendous variances. Thereby, we need to build a bunch of isolation trees and predict each point's anomalousness as a mean value of individual trees' predictions. As amount of individual trees grows, mean anomaly score quickly converges to a reasonable value for each object. Creators of IsolationForest state in their paper that empirically 100 isolation trees is more than enough for the algorithm to converge. Let's demonstrate IsolationForest usage in Jupyter Notebook. We will take a large Gaussian as our data and try to find outliers in it. Let's use Skylon Ensemble IsolationForest to feed an isolation tree. By looking at produced heatmap, we notice a couple of strange things. Firstly, the anomaly scores range roughly from -0.9 to -0.3. While there are not exactly node depths, they are proportional to them in a sense. Secondly, there is a large white homogeneous rectangle corresponding to low anomaly scores. But when we were fitting a tree by hand, we could see that the further down the node is, the more its share of plane is partitioned. So the rectangle should have multiple different subregions of extremely small sizes, forming a mosaic-like pattern. Yet it doesn't. These peculiarities are caused by default hyperparameters and built-in mechanics used in Skylon implementation. These are based on the original paper, and I will walk you through them now. Let's take psi objects out of data and build an isolation tree on them. Mean depth of a leaf in it is logarithm of psi. When detecting anomalies, we are interested only in objects whose node lengths are much below average. Thus, we will stop building an isolation tree once it reaches the depth of logarithm of psi. Normal points will now stop getting scores post logarithm of psi, but the ensemble scores will still converge to a high number. Wait, where did psi come from? Why don't we build isolation trees on all the n objects? There are two main problems IsolationForest may face. Swamping is a problem of anomalies being located very close to one normal cluster, and thus being harder to separate. Masking is a problem of anomalies forming a dense small cluster, also causing the separation to become harder. But what will happen if we subsample? We are likely to pick a small number of objects near normal cluster's body, making nearby outliers easily separable if picked. Thus, swamping is solved. As anomaly clusters are small, we will select very few points from them, so masking is also solved. Authors of paper state that empirically the best value for psi is of order 2 to the 8th, meaning individual trees grow to depth no larger than 8. Let's imagine the following scenario. Our tree is built on 2 to the 8th objects, and a few of them are isolated before reaching depth 8. The resulting leaves may have strongly varying numbers of objects in them. The more objects in a leaf, the more the anomaly score is undervalued. A way to paraphrase the problem is we haven't built subtrees corresponding to some areas. As we do not need precise results for these areas, we can roughly estimate the anomaly scores by term C of n, where n is the amount of objects left in the node and is at least 2. The term has the order of logarithm of n, so it is proportional to mean tree depth built on these objects without using the hyperparameters specified above. There is an easy way to see C of n at work. Suppose we have a dataset of 4 points and we have built the following tree on them. The root node divided objects 3 to 1 across x. Its left child divided the objects 2 to 1 across y. As max depth for tree with 4 objects is 2, we can't add more nodes. Yet, as we can see, the objects in left child's upper node score more than the objects in left child's lower node. That's because the upper node has more objects and thereby bigger C of n term. The reason why Scalone ensemble isolation forest scores are between -1 and 0 is that all the scores are compressed into this interval using following function. This means for outliers the score will be close to -1, and for normal objects the score will be close to 0. As for contamination hyperparameter, in auto mode outliers are determined by threshold -0.5. Specific values allow us to set this threshold dynamically, so that outliers fraction is equal to contamination. To sum up, the large homogeneous rectangle on the heatmap for built isolation tree corresponds to max depth of that tree and can no longer be divided. Although individual trees are noisy, the predictions improve greatly when the trees are stuck together. Isolation forest with 100 trees produces heatmap corresponding to the Gaussian score points very precisely. Thus, isolation forest algorithm can be a useful tool to approximate outlier distribution in your data. If you want to have a look at outlier profile, give it a go.